We're at Pratt and Whitney Media Day with Dr. Alan Epstein. Alan, could you walk us through the idea of the D8 engine that we're hearing about?
Yeah, MIT, Pratt and Whitney, and Aurora Flight Sciences teamed up to respond to the NASA N+3 solicitation. And the goal there is, current airplanes are N, next one will be N+2, N+3 would be airplanes for the 2030s. And the goal was 70% reduction in fuel burn, and such an enormous reduction in noise that the cars driving up to the airplane are noisier than the airplane. And the D8 was the successful advanced design the MIT aerodynamicists came up with. This is an engineering program, so it has no great names. It looks like a D because instead of being a round fuselage, you look at the fuselage in cross section, it's a D. It's flat on the top with a rounded bottom. It's a small twin aisle size as a A320, 737 size at the curve. It has very straight wings using advanced aerodynamics, and has a 70% reduction in fuel burn compared to an existing 737.
Now, the way that the structure of the airplane looks in the pictures, you've come up with a very novel approach to the engine.
Yeah, well, novel approach to the engine and the functionality of the engines. Since the first jet airplanes, really since the 747, the B-52, and then the commercial 707s, the airplane people have tried to divorce themselves from the engines. They've hung the engines on pylons from the wings. And actually that was the lesson of the B-17 from World War II, which is an engine would seize up in combat and then tear the wing off. And so the Boeing engineers had the idea of hanging them from wings on pylons, so if in combat the engines hung up, they'd fall off. But it had another effect, which is you could engineer the engines separately from the airframe to a large degree. And it made the whole problem a lot easier. But it gave up potential in performance. And so in the case of the D8, the engines are positioned right on top of the fuselage at the very back. So the boundary layer that builds up over the fuselage, and it has much more fuselage now because it's flat and it provides a lot of lift compared to a current airplane, that goes through the engines. And the engines end up then canceling the wake from the fuselage. And that weight cancellation is worth 6, 8, 10% in fuel burn. So instead of having a wake as the airplane goes by, there's nothing. The engines have canceled it out. That's the good news. Good news for the airplane guys. For the engine guys, we have a bunch of challenges. One is the air coming into the fans now is highly distorted, something we've avoided. In fact, conventional installations are really good for giving us clean air. And rather than avoiding it, for the D8 we have to embrace it. So one question is, how do you design fans that can take really distorted air, provide high efficiency, and aeromechanically, vibration-wise and noise-wise, be in great shape? And so a separate contract to the United Technologies Research Lab, which is only 100 yards in that direction. They've been working with NASA designing such fans for us, and that looks very favorable indeed. The next challenge is the engines have to be very close together so that they swallow the entire airframe. From safety considerations, in the late 90s, the FAA set an advisory out that said, in the extraordinarily rare case that an engine might blow up and a major segment comes out, it's called an uncontained failure, there has to be a very low probability that it will result in a disaster. And it's called the 1 in 20 rule. And so if the engines are very close together and a part flies off, then it might take out the next engine. For a military airplane, it's less of a problem because you have ejection seats. I don't see ejection seats going to commercial airlines, and maybe if you don't pay or whatever when you come down the aisle. So we needed a configuration that maintains safety, but also weight. And so, yes, you could think of heavy armor between the engines, but that's A, inelegant, and B, heavy. We note that as the engines have advanced, the fans get bigger, the cores get smaller. The cores are getting very, very small, even on the GTFs. If you look at the size of the core versus the JT8D, in area it's only 1/10 the size, because the engine's a lot more efficient and the air is compressed to a higher density. So some very clever designers here figured out, we could angle the back of the engine. If we reverse the flow as Pratt did on the PT6, which everybody thought was sort of silly in 1958, but here it's still in production. We make thousands a year. There's 40,000 of them flying, so maybe it wasn't such a bad idea in 1958. So this is the revenge of the PT6. It's a large engine where the core input pours backwards. Flow comes to the fan. The small amount that relatively has to go through the core turns 180 degrees, goes to the core. The core now blows into the low pressure turbine, which is coupled to the gear and coupled to the fan. There's nothing connecting the core and the low pressure spool now but an air duct. So we can make the air duct at an angle. And we have two engines like this. If a part comes out of one, it doesn't intersect with the other. 1 in 20 roll. So it looks kind of strange, but it has a lot of advantages because the core isn't connected now. The shaft doesn't go through the core anymore. There's nothing connecting the core to the big fan, low pressure turbine gear. I can just drop the core off as a line replaceable unit for maintenance. I can, when the airplane's sitting on the ground, I can take the core off. It's a great, we turned to a necessity, which is how do you satisfy safety? And how do you get a big shaft or a very tiny core into a virtue? And all you got to do is convince everybody else that it looks great as opposed to crazy. And we're pursuing it with NASA support. There's been a large D8 wind tunnel test down at NASA Langley, which has been very favorable. And we're working with some airframers looking at how it might go forward.
Thank you.
Thank you.